Reactor Probe TBA, Josh Currens, Robert Kempin, and Bradley Moreau.
Project Summary. We were given the problem of measuring the power output of a nuclear reactor solely from the intensity of the Cherenkov radiation emitted by the reactor core. Our design constraints required us to build the probe for under $40, make sure the probe was completely waterproof, and avoid damaging the reactor in any way, shape, or form.
Nuclear reactors are devices that use nuclear fission, or the splitting of a radioactive nuclei, to generate massive amounts of energy and heat. Nuclear reactors commonly use uranium, splitting the unstable U-235 isotope. This fission releases neutrons, which then impact other atoms, continuing the chain reaction. Reactors use control rods to moderate the rate of reaction and ensure safety. In commercial reactors, the excess heat is used to make steam and turn a generator to produce electricity. Small reactors, such as NC State's Polestar, are used as research reactors and produce no electricity.
Cherenkov radiation. Similarly to sound, the speed of light varies by medium. In water, the speed of light happens to be around 77% of the speed of light in a vacuum. Because of this, charged particles are able to exceed the local speed of light. When particles are traveling faster than light in a dielectric medium such as water, an effect similar to a sonic boom is produced. This interaction excites the water molecules, which then radiate visible light that we see as a brilliant blue glow in the reactor pool.
The first step in the engineering design process is to ask. So we asked ourselves what we had to accomplish. Our project assignment was very clearly defined. We had to build a watertight probe capable of measuring the light given off by NC State's Polestar reactor, and use those readings to find a mystery power level, based only on our measurements. As with any engineering project, we had several design constraints. We were required to build the probe out of unpainted PVC pipe, under 2 inches in diameter and under 12 feet long. The probe had to be completely watertight, safe to the reactor, and built within a total budget of $40. As a part of the ask portion of the design cycle, we also agreed on our team's goals. We wanted to find the power level within 2.5% accuracy and be competitive with our peers on FEDD.
The second step is imagining a solution or brainstorming. As a team, we recognized our design constraints left little room for variation in design and decided that we should focus on high build quality for reliability and accuracy. As a part of our brainstorming process, we conducted a lot of group and individual research and met several times to gain a thorough understanding of our project.
Designing the probe. The third step of the engineering design cycle is planning. As a team, we planned our entire design and set strict deadlines for ourselves. The most important aspect of the design was deciding on the sensors we would use. We settled on 2 photodiodes operating in zero bias or photovoltaic mode, giving us a simple and accurate measurement.
The fourth step of the design process is create. In our project, the construction was relatively simple. The photodiodes were placed through a piece of foam at the base of the probe, and wires were run the length of the PVC pipe. The cover was made of polycarbonate tightened against a rubber O-ring at the base of the pipe to ensure a watertight seal. The probe was split into 2 sections that could be disconnected for an easier transport configuration.
The fifth and final step is improve. We tested our probe using incandescent lights to ensure proper electrical connections and working sensors. Multiple sensors were used in the probe for redundancy, and the probe was submerged to ensure it was watertight before test day.
Obstacles overcome. As a team, we had to overcome a few obstacles while we were building our probe. We initially found little data and research on the connection between Cherenkov radiation and reactor power level. After conducting much more research, we found that the intensity of the blue glow was directly proportional to the reactor's power level, allowing us to use standard statistical analysis with our data. Overall, the project was not difficult, but did require a fair bit of effort and teamwork.
On test day, we showed up bright and early to Burlington Labs, home of NC State's reactor program, Polestar. With the help of the reactor staff, our probe was secured to the top of the reactor looking down into the core. The lights were then dimmed, and the reactor was set to various power levels as we took our readings. After taking the last reading, the probe was confiscated to be decontaminated before FEDD day.
After test day, we had 3 known power levels and corresponding readings in volts from our probe. Using these 3 data points, we were required to find the unknown power level using the fourth voltage from test A. We found the relationship between our data points was logarithmic, so we used a logarithmic regression and calculated the unknown power level to be 999.8 kilowatts. We later learned that the mystery power level was 1,000 kilowatts, giving us a 0.011% error, which was well within our target of 2.5%.
On FEDD, we arrived at McKimmon Center to set up our trifold presentation and probe to display our project to the judges and visitors. We were then judged based on our results and probe design. After the judging and scoring were completed, Team TBA was announced the winners of the morning FEDD Fall 2017 session.
As a team, we learned several valuable lessons over the course of this project. First, the engineering design cycle is necessary when approaching any engineering problem or project, and every step of the cycle is just as important as all the others. We also learned that teamwork is a priority and absolutely vital to success. Should we do this project again, we would definitely keep track of time and hold ourselves to our planned schedule better. We would also secure the sensors in place within the probe body to keep them from sliding down the probe. Furthermore, we would order parts earlier to ensure that all components arrive with plenty of time to spare. And finally, do not apply PVC cement in your dorm room. Your roommate will thank you.
Lastly, Team TBA would like to thank Dr. Lisa Marshall, our project guru, for her guidance and time spent assisting us and the other nuclear probe teams. We would also like to thank the reactor staff for their patience and time spent allowing us to test our probes in the reactor.